All right, section 3.7, rates of change in the natural sciences. So over the course of the next few sections, we're going to deal with a little bit of application. We're going to start putting the derivative to work for us, okay? So obviously, you have to be a little careful with your wordings and again, our understanding of the, in this case, the different derivatives that we've talked about, our starting with our position function and then its derivative, the rate of change in position, which is your velocity function, and then the rate of change in the velocity, which was the acceleration function, which also then ultimately is the second derivative of our position function. All right. So we're going to work with those particular functions primarily in this section, and kind of just make use of those functions in terms of information that they give us about, in our case, the motion of a particle, the motion of an object. Okay. Also be careful of units. I'm always a stickler for units when it comes to application problems. So when we're talking position of an object or our position function, we would have units like feet or meters or inches, that type of thing, right? What is the actual, I call them linear measurements. Linear displacement is another term we use there. Then our rate of change in the position, remember velocity is change in position over unit of time or per unit time. So it's change in position over time, so you get units like feet per second, miles per hour, meters per minute, that kind of thing. And then when we talk about acceleration, again, since acceleration is change in velocity over time, then we get units like feet per second, or feet per second squared, or like meters per minute, right? Or meters per minute squared. So you're just going to raise the exponent on that time unit, and that's due to the fact that each of these is a change in the previous measurement over time. Right? So you're always just increasing the time unit. So keep that in mind. We want to make sure we use appropriate units anytime we're dealing with applications. All right, so for this particular example, I have a straight a question or a situation we're going to deal with, and we have a bunch of parts to this thing. So I'm starting with the position of a particle given by that function s of t equals t cubed minus 9t squared plus 15t plus 10. And so our position function, where t in this case is measured in seconds and s is measured in feet. Question part A, find the velocity at time t. That's a pretty straightforward question, right? Finding the velocity at time t. We're just finding our velocity function, which we, as we already know, is the derivative of our position function. So I'm just going to differentiate, find v of t, which would be the derivative of s prime of t, and that's a pretty straightforward little power function. Right? It's a polynomial, so using the power rule, 3t squared minus 18t plus 15. And then we have units on that function because it is velocity, in this case feet per second. Now, I mentioned this to you before previously that, with the function itself, if you don't include the units, I'm not going to make a big deal about that. Now, once we do actually plug values into that function and we're coming up with a specific measurement, then yeah, I absolutely want to see those units. But, you see the units included here just simply because it is a velocity function whose units would be feet per second. All right, but if you don't include those units, I'm not going to dock you for that unless we're actually plugging in a value and I'm looking for a specific velocity with respect to a specific value for t, as we have in part B, all right, which says what is the velocity after 3 seconds. So there I'm just plugging then 3 into our velocity function that we just found, or s prime of 3. All right, and again, I don't care which way you label it. I like using v of t obviously because it's velocity. But we use the derivative as well just to remind us of what that is, right? It's the derivative of our position function, but either notation is fine. And if you plug 3 into that velocity function, you will get a value of negative 12. Now again, our units there, feet per second. So the velocity of this object, of this particle, in this case, is negative 12 feet per second. Now we've mentioned before, because we talked about velocity early on in relation to kind of a direction component now. I think the example we had early on was with a rock that you're throwing up into the air. And we said it would have positive velocity when it's rising and then negative velocity when it was falling. So kind of the same idea here. Since the velocity here is negative, I'm going to use the context to say moving forward or moving backward, right? So from some frame of reference, if you're moving forward, your velocity would be positive. If you're moving backward or in reverse, let's say, your velocity would be negative. So the fact that the velocity is negative here means that at 3 seconds, our particle is moving backward. We'll talk more about that as we go forward. Question part C. When is the particle at rest? Okay. So I want to know when that particle is not moving. Well, a logical observation, when is the particle not moving? Well, when its velocity is 0, right? So here's our interpretation of that question. When is the particle at rest? It's at rest when its velocity is 0 because it's not moving, okay? So we'll take our derivative, which is s prime, and set that equal to 0, or again, that's our velocity function, and set it equal to 0. So here, of course, you want to be careful in terms of which function you're working with. We have our position function. We have our velocity function. We're also going to talk about acceleration. So you're going to have 3 different functions that you're working with, so please be careful. Make sure you're actually using the correct function to answer the question. All right, so here I want to know where velocity is 0, so I'm setting our derivative. Call it s prime, call it v of t, and I want to know where that is equal to 0. And then we're setting up that equation, and we're just going to solve that equation. All right, now this is a nice little polynomial equation. First thing I did was factor out the 3. Just to remind you of that. So if I factor out the 3, and then I could actually divide both sides by 3. 0 divided by 3 is still 0. So that's why I didn't bother including the 3 here. And then we factor the t squared minus 6t plus 5. And of course, basic factoring of polynomials, we need to make sure we're able to do that. Or of course, you could use quadratic formula here. Remember, this is a quadratic equation. You could plug that into quadratic formula if you prefer, if you don't like the factoring. But we'll run across most of these that will be factorable in form. Not always, but I think the large majority of them will be. But regardless, I'm just solving that equation, whatever is necessary to do that. So I factor, I get t minus 1, t minus 5 equals 0. Set each factor equal to 0, and I've got t equals 1 and t equals 5. And again, I know I'm skipping some of the basic algebra here, but I trust that you remember how to solve a basic polynomial equation. All right, so we set each factor equal to 0. We get our values for t. So now t in this case we said was measured in second. So where did those t values come from? It came from setting the velocity equal to 0, which we were looking for where the particle was at rest. And so we know the particle is at rest. It's not moving at t equals 1 second and at t equals 5 seconds. Okay. Next question. When is the particle moving forward? Or I could just as easily ask you when it's moving backward. Well, again, from what we were just talking about in terms of the velocity and the sign of the velocity function, we just found where the particle was not moving, where it was at rest at t equals 1 second and t equals 5 seconds. When would the particle be moving forward? Well, it's moving forward when its velocity is positive. And it's moving backward when its velocity is negative, right? That's what we said earlier. So we're assigning a sign component to our velocity function, positive velocity moving forward, negative velocity moving backward. So in this case, we're interested in where the particle is moving forward, or in other words, where then the velocity is equal, or greater than, greater than 0. Now, I'm going to give you an algebraic process for answering or going about solving these types of questions. And then we're also going to look at kind of an observation from the graph and why this works the way that it works. Okay, but this process may ring a bell if you remember from algebra when we find critical values of numbers and this type of thing. But I'll remind you of what we're doing here, why we're doing it, and why it works. And then after that, we're just going to use the process. Right? So I'm going to do a little graphical a graphical observation, and then look and see why this process works in determining these values for, in this case, our velocity function, because we want to know where velocity is greater than 0 or where it's positive in this case. All right, so what we do is, all right, so we said we were interested in where s prime is positive, so we start with the same equation that we just had earlier. I include the greater than here because that's what we're interested in. But if I want to know where this velocity is positive or where it's negative, whichever way we want to go with that, the first thing I'll do is I'll find where the velocity is equal to 0. So basically we solve the same equation that we solved earlier. We factor, we got t equals 1 and t equals 5. We know where that velocity is 0. So on this little number line that I have over here on the right, here's t equals 1, here's t equals 5. We know at those points velocity is 0, and we want to know where the velocity is positive in this case. So what you're going to do is you're going to take those values that we find for part C, where the velocity is 0, and we use those to set up what I call a test strip. It's nothing more than a number line, and I indicate on the number line those values that we found, where in this case velocity is 0. Okay? Now, before I proceed with the algebraic part of it, let's look at the graph of that function. This velocity function, s prime, 3t squared minus 18t plus 15, that's just a basic quadratic function, right? Its graph would be a parabola. Now remember, this is our velocity function. So if I look at the graph of that function, where is that function positive? Well, it's positive here above the x-axis. And the function is negative where the graph falls below the x-axis. Right? I mean, that's just basic observation about the graph. So the value of the function is positive where it's above the x-axis. The value of the function is negative where it's below the x-axis. So now we found the x-intercepts. Remember, that's where the function is equal to 0. So again, I'm going back to some basic algebra here. So what we actually found with respect to the graph of this function in part C, we found the x-intercepts. Where is the function equal to 0? And so at t equals 1 and t equals 5, those are the x-intercepts on the graph of that function. And then what I'm interested in is, notice between each of those x-intercepts, here and here, what's the value of the function? Is it positive or negative? Now, this also relies upon continuity. We talked a lot about continuity. Provided that the function or the graph is continuous, then the only way that this graph could change sign, in other words, the only way that the graph could go from being positive to being negative is if it passes through an x-intercept. Okay? And vice versa. It'll go from negative to positive only if it passes through an x-intercept. So once we find those x-intercepts, and provided that our function is continuous, then I know that the only place that that function can change sign is on either side of those x-intercepts. So what we do is, once you set up your test strip, locate those values where the function is equal to 0, in this case it's our velocity, and then what I'll do is I'll just choose a test point out of each of those intervals. You can pick any number between 0 and 1. Now, starting at 0, because remember, t is time in seconds, right? So t is the number of seconds after we start observing the motion of our particle. So by default, we want to start at 0. So I've got an interval from 0 to 1 second. We know the particle is moving in a certain direction because at 1 second it comes to rest. Then we have this interval from 1 to 5. I know the particle is in motion. And then again, at 5 seconds, it comes to rest. So again, if I take any value between 1 and 5, I just chose 2. You can pick any number, doesn't matter, any number in that interval. Whatever the sign of your velocity function is at t equals 2, it's going to be the same as the sign of the velocity for any value in this interval, right? If I plug in 3 or 4. And that's all I care about. All I care about is where this function is either positive or negative, because positive value is a positive velocity moving forward. Negative value is our negative velocity. We said that's moving backward. And remember, that's what we're looking at here. We're looking at the velocity function. So back to our 1/2. If I plug in 1/2, I get a sine, S-I-G-N, of that function. It should give me a positive value. If you look at the graph, it's above the x-axis. But all I'm doing is I'm plugging that 1/2 into this velocity function, into our derivative. I don't even care what the number is. All I care about is whether it's positive or negative. Now you can do this one of two ways, and this is all just how you care to do it. You know, I'm plugging it into S prime. That's this function. So you can always just plug it in there and get the value. When I have a function in factored form, if you want to, you can do it a little bit quicker even without typing all that stuff into your calculator. Because if you look at the factored form, if you plug in 1/2 into t minus 1, you're going to get a negative number, right? 1/2 minus 1. You plug 1/2 in here, you're again going to get a negative number because it's 1/2 minus 5. So I've got a negative number times a negative number, which gives me a positive number. So you can always kind of use the factored form as a quick calculation because, again, all I care about is the sign. I don't care what the number itself is. So we repeat this process through each of those subintervals. So for the interval from 0 to 1, I pick any number in between those two. I picked 1/2. Plug it into your velocity function to see if it's positive or negative. In this case, it's positive. Then I pick a number in the second subinterval between 1 and 5. I chose 2, but again, you could pick any number between 1 and 5. And if you plug 2 into that, again, velocity function, you will get a negative value. Now notice if you go over here to that factored form, when you plug 2 into this factor, 2 minus 1 is positive. Plug 2 into this factor, 2 minus 5 is negative. So you got a positive times a negative, that gives you a negative value. Right? So that means our velocity there is negative. And again, if you look at the graph, between 1 and 5, it's below the x-axis. It's a negative function value over that interval. And then we finish it off. We pick the third, we look at the third interval, pick any number greater than 5. I chose 6. You could just as easily choose 7 or 10 or 100 or any number that you want as long as it's in that interval. And you plug that into your velocity function. And as we see from the graph, we should get a positive value. But again, if you come over here to the factored form, if I plug 6 into this factor, 6 minus 1 is positive 5. Plug 6 here, I've got 6 minus 5, which is positive 1. So I've got a positive times a positive, which is positive. All right, so, you know, in other words, there's a lot of different ways you could do that. But again, bottom line, here's a quick recap. What do I do? So I have a function that is continuous over the interval of which I'm interested. And in this case, it's polynomial, continuous everywhere. So I want to know where this function is positive or where this function is negative. In our context, it's velocity, positive velocity moving forward, negative velocity moving backward. So we start by finding where the function is equal to 0. And so that's what we did in part C, the previous part. Once you find where the function is equal to 0, that then divides your little test strip down here into subintervals. So I use a test strip, I call it. I just indicate on that number line where the function is equal to 0. And then we pick a number in each of the intervals that are set up by that test strip. You plug those test values into your function to check to see if the function is positive or negative. And then we pick whichever interval answers our question. So in this case, we wanted to know where the particle was moving forward, where the function was positive. So on that interval from 0 to 1, and then also on the interval from 5 to infinity, in this case, t greater than 5. Right. Now again, you can always graph it and use a graphical observation to see very quickly where the function is positive or negative. Now you do have to be able to identify those x-intercepts. Right, so I have to know what those are. So that's a case where we're using the derivative to give us information about, you know, the object, in this case, the particle. So using the first derivative to determine where the object is moving forward or backward. Okay. We're going to do some more with this as we go forward into chapter 4. And so this is kind of laying the groundwork for some things that's coming a little bit later. And we're going to use our derivatives, our first derivative, our second derivative, to give us information about what the graph of a function looks like. And so this is the kind of thing that we're going to be doing, setting up these little test strips and checking the values of our function. Part E, find the total distance traveled by the particle during the first 8 seconds. All right, so now we've talked about this idea of distance previously when we first introduced the idea of position and velocity and acceleration. We talked about distance versus displacement. All right, so when I talk about displacement, that is, we call it this kind of like the straight line distance, as we say, as the crow flies, from point A to point B. From where we start to where we stop. What's that straight line distance? That's our displacement. How do we get from point A to point B? Well, that can change, right? You can take a direct route along a straight line, or you can take a scenic route. Think about just going from one place to another in a vehicle, right? You got to make turns, you got to go through curvy roads and this kind of thing. The displacement as the crow flies from point A to point B is maybe a straight line, whereas your total distance traveled is going to be different. So be careful. It's the language, displacement versus distance. In this case, we're looking for the total distance traveled by our particle. Now, what we already know is that particle moved forward, we just found in part D, on the interval from 0 to 1 second. And then it reversed course and it moved backward on the interval from 1 to 5 seconds, and then it reversed course again and moved forward after 5 seconds. So in this case, from 5 to 8 seconds. We're asked only about the first 8 seconds in this case. Now, what we also know, based upon our observation from the previous section, the particle moved forward on the interval from t equals 0 to t equals 1. So what I want to figure out then is, well, what's the distance that it traveled over that time interval? So it was moving in a forward direction. What is its displacement? So we're just looking at the change in its position from t equals 0 to t equals 1. And that's where our position function comes in, right? Because remember, s of t is the position of our particle. So we find its position at t equals 1, we find its position at t equals 0. And again, I'm using s in this case, so watch which function you're plugging it into. That goes back to our original function s of t from part A. Or from the original question, actually. So if I plug in 1 into our position function s, you get 17. You plug in 0, you're going to get 10. And we're looking at the distance between those two, so 17 minus 10. Now the reason for the absolute value is because I'm not interested in which direction the object was moving here. I'm asked for the total distance traveled, right? So ignoring direction, so if I put absolute value on these calculations, then it doesn't matter which direction we're moving, the value will always be positive. That gives me a displacement of our particle. So it's located at 17 feet, would be our unit there, at 1 second. It's located at 10 feet. And again, this is with respect to our frame of reference, so s of 0 is 10, s of 1 is 17. And then the difference between those two then is 7 feet. So over that time interval, that tells me that our particle has traveled a distance of 7 feet. Now again, I'm using s of t. That was our original function, right, here. The t cubed minus 9t squared, etc. All right, so that's why I keep saying you're going to be working with multiple functions. Make sure you're plugging it into the correct function. And then we just repeat that over each of the time intervals that we found in the previous section, or previous parts. So I know then that from t equals 1 to t equals 5, the object is moving backward. We found that in part D. So what is the displacement? What is the distance traveled? Take its position at t equals 5, which actually gives you negative 15. You take its position at t equals 1, which we already knew from the previous part, was 17. Take the difference between the two, so negative 15 minus 17, that's going to give me negative 32, but again, the absolute value gives me a positive 32. That's the distance traveled over that time interval, right? So all you're doing is you're calculating change in position over each of those time intervals that we found in the previous section, because we knew where the particle was at rest. I don't even care where it's moving forward or backward here. All I'm interested in is between each of those points where it's at rest, what is the distance that it traveled to get from point A to point B. So from 0 to 1 second, we found the distance traveled of 7 feet. From 1 to 5 seconds, 32 feet. And then we said it was moving forward after that. So from t equals 5 to t equals 8, because that's where we're asked to cut this off. So find its position at 8 seconds, which gives us 66 if you plug that into s of t. Find our position at 5 seconds, which we had previously at negative 15. Now again, we're looking at the distance between those two, or the difference in between the locations. So notice we're always subtracting there. So it's 66 minus negative 15, or 66 plus 15, which gives us 81, absolute value of which is 81. So that's giving me the distance traveled over each of those time intervals. And it's simply change in position over each time interval. And then we take the sum of those three to give us the total distance traveled of 120 feet. Now again, that is distance different from displacement. If I asked you what was the displacement of that particle over the first 8 seconds, that is straightforward. Where was the particle located at t equals 0, and where was the particle located at t equals 8? And so s of 8, again, which we just said was 66, s of 0, which was 10, that's our starting point. And then again, we take the difference between the two. Where did it finish? Where did it stop moving, over the time interval? Where did it start? And I get a difference of 56 feet. Now again, that's the displacement of our particle as the crow flies from point A, where it started, to point B, where it stopped, or at least where we were observing it over that time interval. And that's different from total distance traveled. Part F maybe illustrates that even a little bit better, because there we're drawing a diagram to represent the motion of the particle. All right. So with respect to, and on our number line, that's our position. So I have this labeled as s of t. And you always want to be, just make sure everything is labeled. You just need to be clear, learn to label things. I keep telling y'all, it's organization. You have to clearly label things so when you look at it, you know exactly what you're talking about. And now that we're working with multiple functions in the same problem, that's even more critical. So that number line at the bottom represents our position. And then we're traveling, starting at time t equals 0. So s of 0, which we said in the previous part, was 10. So I'm starting at a location of 10 feet from, we're calling this maybe our frame of reference, at t equals s of, don't even call it that, just a position of 0. All right, so with respect to our frame of reference, if we're maybe standing at 0, then at s of 0, when we start observing this particle, it's at a distance of 10 feet from that location. And then notice the particle was moving forward over the interval from t equals 0 to t equals 1. So our particle moves forward, then at t equals 1, we found that our particle was located at 17 feet. Right? So s of 1 was 17. And that's where we said previously, that's where the particle came to rest, was at t equals 1 second. And notice, if you're going to change direction, if you're going to go from moving forward to moving backward, what has to happen? At some point, you have to come to rest at a specific instance in time. You can't just automatically go from moving forward to backward, right? So you have to reach a point of rest, some instantaneous point or time, where you actually then can change direction. Now, just because you hit a time where you're at rest doesn't necessarily mean you're changing direction, right? I mean, I could move forward and then stop and then move forward again. But I know that if there's going to be a change in direction, there has to be a point of rest, okay? And so that's why we found our derivative and looked at where the velocity was 0, because we knew then that could be a possible change in direction at that particular time. I'm going to come back to this and talk some more here about another observation once we get done with this part. So that's our position, or distance traveled from t equals 0 to t equals 1. Then we're at 17 feet. And then we said the particle changed direction because from t equals 1 to t equals 5, we said the particle was moving backward. So we found s of 5 previously. S of 5 was negative 15. So our particle changed direction. It moved from 17 feet back to negative 15 feet. All right? And remember, that's what, if you look at that second calculation at the top, from t equals 1 to t equals 5, remember we found that it moved the distance of 32 feet. And if you go from 17 feet to negative 15 feet, that's a distance of 32 feet. 17 positive and 15 in the negative direction. And then when we hit t equals 5, again, we hit a point of rest. So where velocity was 0. And then our object began moving forward after that. And so we had found s of 8, which was 66. So at t equals 8, we're located at a position of 66 feet from our point of reference. So over that interval from 5 to 8, the particle was moving forward from a location of negative 15 feet to a location of 66 feet. So that kind of, even better illustrates the behavior of this particle, right? So it's moving forward, then it's moving backward, then it's moving forward again. And we have indicated those points at which we had that change in direction. Question part G. Find the acceleration at time t and after 4 seconds. So again, that's pretty basic. We've done that kind of thing before, right? So we want our acceleration function, which is the derivative of the velocity or the second derivative of our position function, right? So our position function s of t, our velocity was the derivative s prime, our acceleration is the second derivative s double prime. So I find our second derivative, I get 6t minus 18. Now again, there's units on that. It's feet per second squared. Remember, we said acceleration, change in velocity over time. So feet per second, or feet per second squared. And then we're just evaluating, plugging in 4 in this case. So it is a velocity after 4 seconds. So I've got a of 4. Yes, double prime of 4, which would give you 6 feet per second squared. Right. So I have positive acceleration in this case. Now, again, there's a direction component to acceleration. Now, we'll be a little careful. You're going to get into the next part. I'll explain a little bit more about that. But positive acceleration, negative acceleration. Positive acceleration maybe means I'm speeding up in that positive direction. I'm moving forward faster. If my acceleration was negative, that could I think that kind of takes on two different meanings that we'll see. You think of positive acceleration as speeding up, you think of negative acceleration as slowing down. May not absolutely mean that. Okay? So like I said, when we look at these next couple of parts, we'll maybe have a little discussion on that. But regardless, here I get a positive acceleration, 6 feet per second squared. So the next thing I did was I graphed those 3 functions that we've been working with. The position function, which was s of t, we had our velocity function that we found, s prime, and we now have our acceleration function, s double prime. And I graphed those 3 functions over the interval from 0 to 8. If you want to look at this on your calculator, there's a window setting. Right, so along your x-axis, if you want to go an x-min of -1, x-max of 8, I just do the -1 so that I actually see the y-axis when I graph the function. So we're graphing over the interval from 0 to 8, technically. And then over the y-axis, I did -20 to 70. Again, the -20 is just so I can actually see the x-axis and I can see those functions. And then a y-max of 70. So just recommended window settings. So there's the graph of our 3 functions. Now, if you remember what we know about the basic shapes of the graphs, a that we just found, acceleration, that's a linear function, right? A of t was 6t minus 18. So there's a of t. It's the linear function. It's this guy. We already mentioned earlier the velocity function, s prime, was a parabola. So there's our velocity function. So that means then this other function, this third function, is our position function. So there's s. Okay? So I'm going to ask you a question next, and we're going to refer back to these graphs to get some information. or at least make an observation. So question part I is the last part of this particular question. Where is the particle speeding up and where is it slowing down? Okay. So we already answered the question, where is the particle moving forward, where is it moving backward? And that was strictly an observation about velocity. Positive velocity moving forward, negative velocity moving backward. But where is it speeding up, where is it slowing down? Now I'm going to make an observation first before I look at the graphs we just had. I'm going to go back to this little diagram that we drew up earlier, tracing out the motion of this particle. Let me get this out of the way. Okay. Now think about when this particle is moving. When is it speeding up? When is it slowing down? Well, we know where it has to come to rest. It comes to rest here. It's not what I want. It comes to rest here. It comes to rest here. Well, think about what happens when it comes to rest. Right before it comes to rest, what is the particle doing? It has to be slowing down. So in other words, over this interval from t equals 0 to t equals 1, when it hits that point of rest at t equals 1 second, the particle has to be slowing down in order to stop, right? So I know just looking at this observation that our particle should be slowing down over the interval from 0 to 1 second. So when it hits t equals 1, it can actually then change direction. Now what happens when it changes direction? Well, the first thing it does, it'll start speeding up, right? Because it's moving from rest in this direction, so it's going to start speeding up. Now there's another point at which it comes to rest at t equals 5, so somewhere along the line here it has to start slowing down again, right? So between t equals 1 and t equals 5, for some part of that time interval it has to be speeding up because it just left the point of rest at t equals 1, speeding up, and then at some point it's going to have to start slowing down so that again it can change direction, all right? So then it hits a point of rest at t equals 5, and then what happens after t equals 5? Well, again, it's going to start speeding up because it's coming from a point of rest. Now, it doesn't have any more points of direction change, right? So it's staying in a positive direction or forward direction from that point forward. So notice I'm just speeding up here, or definitely I'm not going to be slowing down again because I'm not going to be changing direction. Okay? So that's just an observation from there. Now, if you look at these graphs, okay, so how can I use the graphs of the functions themselves to give me that information? Well, here's where it's going to go back again. We have to be clear on exactly what you're looking at in terms of function value when you look at the graph of a function. Where the function is above the x-axis is where it's positive. Where it's below the x-axis is where it's negative. And then you also have the value of the function itself. Right? So in other words, if we look at, say, the velocity function, over the interval from 0 to 1, what's the velocity doing? Well, we already know that the velocity is positive there. We said the particle was moving forward in that previous section. But notice, though, what's happening to the value of the velocity. It's getting smaller, right? The value of the velocity function is decreasing from here to here. And if the velocity is decreasing, then what's happening? Well, it's probably going to be slowing down, right? And then we hit that point of rest at t equals 1, and then what happens after that? Well, after that, the velocity becomes negative. But notice over the part that I have highlighted, it's getting larger negative. So that tells me two things. First of all, the negative velocity means it's moving backwards. We've already established that. But then what's happening to the actual value? It's getting larger negative. So the fact that it's getting larger negative means it's doing what there? It's actually speeding up. It's moving faster in the negative direction. And then notice right about t equals 3, what happens? The velocity, it's still negative, so we're still moving in the backwards direction. But the value of the velocity is decreasing. It's getting less negative, which means the object would have to be slowing down. And that makes sense because, again, when we hit t equals 5, we know that the particle is at rest. And then what happens after 5 seconds? Velocity becomes positive, but also notice it's getting larger. Right? The value is increasing. So that's just using the graph of the velocity function to tell me where this thing is speeding up and slowing down. So it has to be slowing down where the value of the velocity is positive and decreasing, as it was over 0 to 1. Then it's speeding up from 1 to 3 because velocity is negative, but it's getting larger negative, moving backward faster. And then from 3 to 5, it starts slowing down. It's still moving backward, but it's getting less negative, so it's slowing down. And then after 5 seconds, it's positive and getting larger, so it's speeding up. Now what I want you to notice is also in connection to the acceleration function. Notice we said, looking at the velocity, that it was slowing down over the interval from 0 to 1. Look at your acceleration over the interval from 0 to 1. Acceleration is negative there. So we have positive velocity, negative acceleration when our particle is slowing down. On the interval from 0 to 3, let me change colors here. Interval from 0 to 3, we said the particle was speeding up. So notice our acceleration from 1 to 3 is also negative. So in other words, I have negative velocity and negative acceleration. Then on the interval from 3 to 5, we said the object was slowing down. Negative velocity. Notice your acceleration in this case is positive. And then over the last interval where we said we were speeding up from 5 to 8, both velocity and acceleration are positive. So there's actually a correlation between the two. So you kind of think of it this way: where you're slowing down, velocity was positive, acceleration was negative. Then I think that makes sense because we're moving in the positive direction with negative acceleration. If you just think of these as two forces maybe acting upon your particle or your object, if they have the same sign, then you're going to be speeding up. If they have opposite signs, you're going to be slowing down. So in that first interval from 0 to 1, right, velocity was positive, but acceleration was negative. We're slowing down. Over the second interval from 1 to 3, where velocity and acceleration were both negative, so we're moving in the negative direction because of negative velocity, but the fact that acceleration is also negative means that it's pulling me in that negative direction even faster. And then the next interval from 3 to 5, where we said we were slowing down, there we had negative velocity, positive acceleration. So we're moving in the negative direction because velocity is negative, but acceleration being positive wants to pull me back in the forward direction, so you start slowing down. To where then at 5 seconds we start moving back in the positive or forward direction. Velocity is positive, acceleration is also positive. Right, so that again makes perfect sense. I'm moving in a positive direction with positive acceleration, so I've got to be speeding up. Now that takes a little bit of wrapping your head around. I know that's a little bit tricky in trying to make that observation, but here's ultimately what happens. And this is not going to be a test question. I'll tell you this ahead of time. This is not a test question. I'm not interested in speeding up and slowing down. I am absolutely interested in velocity and acceleration, and maybe where we're moving forward, maybe at rest, and that kind of thing. All right, but this is again just kind of playing around with these values and what it tells us about the motion of an object. So ultimately then, particle speeding up, particle slowing down. It's speeding up when both velocity and acceleration have the same sign. So either when velocity and acceleration are both positive, because we're moving forward, and velocity is increasing, right, because it's positive. Or when both velocity and acceleration are negative. So we're moving in the backward direction, acceleration being negative, it's pulling me in that direction even faster. Right? So bottom line, if velocity and acceleration have the same sign, you're speeding up. And so then vice versa, if velocity and acceleration have opposite signs, you're slowing down. Okay? So you can run that through your brain a little bit, see if you can make sense with that. Here's another little, let's say example, but just another topic. You'll have one of these in your homework to look at. An economics application of a cost function. So let's call it C of x, C for cost, all right, where x is the number of units produced. So our function C of x, the cost of producing x number of units. First question, if I want to calculate the average cost per unit. All right, now notice some of the different notations that we're using. I want to mix up notation. So average cost per unit. There's that little delta, capital delta C, triangle, means change. So change in cost over change in number of units. So think about, how do we calculate an average? So let's say, for example, I wanted to calculate the average cost of producing an item between the 100th and 200th items. So in other words, to produce from 100 to 200 items, what's the average cost per unit? So we would take the cost, let's try that. We would take the cost of producing 200 units, take the cost of producing 100 units, all right, and we take the difference of the two, and that tells me how much it actually cost to produce the second 100 of our item. And then if I want the average cost, what do? We divide by the number of units produced, right? Which would be 200 minus 100, or 100. Right? But it's always, change in cost over change in number of items produced. So generically, I have C of x sub 2 minus C of x sub 1. So what is the average cost of producing between x sub 1 and x sub 2 units? What's the cost of producing this number? What's the cost of producing that number? What's the difference between the two? So that's our total cost. And then we divide that by the number of units produced, and that's our average. Right? I mean, average is, I think, the one thing we're familiar with how to calculate. But what I'm actually interested in ultimately is what is called marginal cost. So this is the fancy word that's used in economics, in business. Marginal cost is the rate of change in the cost. All right, so when I'm manufacturing an item, what is the actual change in the cost of manufacturing that item? It's called the marginal cost. You hear also terms like marginal profit, marginal revenue. What's the change in the profit as we produce more items? What's the change in the revenue as we produce more items? But since it's rate of change in the cost, well, that's our derivative, right? So here I'm using dc dx because it's the change in cost per change in units produced. That's the rate of change in the cost function, which is our derivative. That's c prime of x. All right, all that discussion we've had about the slope of the tan line. We use the slope of the tan line to give us the slope of the curve. What's the rate of change in that tan line? We can use that to give us the rate of change in the actual curve, right? So c prime is the rate of change of the cost function with respect to the number of items produced, right? It's always change in cost per change in item produced. So we call that marginal cost, and then in basic context, what that gives you is, and this is a very important piece of information in manufacturing, what is the actual cost of producing the next unit, right? So now that's different from average cost, because average cost tells you the average cost, obviously, of producing each unit over, say, a product run, between 100 and 200 like I had earlier. And what was the average cost of producing each of those units? But this question would be something like, if you produce 100 units, what would be the cost of producing the 101st unit? If you produce 200 units, what would be the cost of producing the 201st unit? So in other words, how much is it going to actually cost to produce the next unit? Right? Not just the average cost, because the average cost takes a lot of things into consideration. Okay, so that's a good little economics application. The term marginal and what that means, it's just nothing more than our derivative. It's the rate of change in our cost function. In context, it's the cost of producing the next unit or the next item. Okay, so see what you can do with that one in the homework. It gives us a little bit of application. That's it for that section.